Hi, I'm Ben. I'm going to be showing a Datapack I've made. I actually made this like 2 months ago or something like that. It's been a while. It is finished. It's done. It's just not like cleaned up. But I think the things in it, work well enough that they are showcaseable, and maybe you could learn some stuff from them. What I've made, probably should start off with that, is a data pack that predicts where entities are going to land just given their initial velocities in motion and stuff. So you can shoot an arrow and it will predict. It'll just immediately say, yep, right there. And right now I've just had it summon a baby slime that it immediately kills. Um, Fun life for that slime. But it's just a marker to show that it knows where it's about to land. So you can see, you can shoot it wherever. You can actually turn on a dispenser. Have those. Sometimes it's very slightly inaccurate. So if you're shooting too fast at the side of a block, it it says it's going to land here, but it really lands like right there, as opposed to right there. Not a big deal. I mean, whatever. It's really just a rounding error. If really in reality it's 0.6 like 5, it's going to round it to 0.7 instead of 0.65, and that's how off it is, you know. You can also, let me open my data pack, just have it make a particle every point that it goes along, so you can trace its exact path. To actually activate this, you just have to execute as snowball, and then you just have to run the function. It's called predict motion, and if I do that, it'll predict the motion, it'll hit it. There's another function called predict shoot, and what that one does is it tries to predict where it's going to land before you've actually shot it. It does that by taking the player's rotation and trying to see where that would theoretically make it land. So a few problems with that is that arrows don't actually always land. They're random. I'm gonna shoot a bunch of snowballs up in the air, and see, I didn't even move my mouse, but they're all in different locations, just because the randomness of actually shooting it is definitely apparent. Predict shoot tries to get the best approximation for where it's going to land. It's somewhat accurate. It's not bad. It's just not super great either. You're probably wondering how this works. Good question. I will warn you, I made this 2 months ago. I don't even know how I got this working in the first place. So just, if my explanation is a bit shaky, or you don't really follow it, that's completely fair. That's on me. All this does, basically, for the most part, it calculates these equations right here. Just say that this line, the blue line, okay, that's the exact motion of the arrow. Just believe me that this is accurate, okay? I've spent way too long making sure of that. What the data pack actually does is it does this. So there's no real way to get there's no easy way. There's no easy, good way to get this exact blue line. So what the data pack does is it approximates it. So every one of these red dots, so those red dots, it calculates those. It has the equation of this path function, and it calculates it at one point. It doesn't calculate it at every single imaginable point, because that is impossible, and no computer can do that. It calculates it at this one point, and then it says, is there a block here? Imagine each one of these grid lines is a block. I can actually... Each one of these intersections, each one of these is a block. Imagine it as a block. It's a square right now because it's in 2 dimensions on desmos.com, but it is translatable into 3 dimensions, okay? This is the intersectional block. Imagine this block right here is filled. It is a stone block, right? Right here it checks, is that a stone block? Obviously I don't want it just to be every single tick, because imagine getting the exact position of an arrow every single tick. So you have a repeating command block, basically says give me the position XYZ of every single, or of this arrow every single tick, so every 20th of a second. Each one of these dots is that position. Here is where you shoot from. then in 1/20th of a second, it's right there. Then 2/20ths of a second, it's right there. 3/20ths, 4/20ths. But the thing about arrows is that you can intersect blocks between ticks, basically, because it's not, because that's just say arrows and entities, and also whenever I say arrow, I mean any entity. This goes for anything: blocks, snowballs, items, experience orbs, llama spit, but it intersects between that. So to make up for that, is it raycasts. It puts a marker here, it looks at this second point, which is up here, and it teleports that marker forward just a tiny little bit. So it teleports it to right there, and then it teleports it right there, and right there, and then right there, etc., all the way up until it gets to that point. Which, after it gets to this point, it does the exact same thing to this one, and then it goes the exact same thing to that one. So basically, anywhere on the red line, it will intersect the block. Unfortunately, this is a good example. It might teleport, it might clip this corner. So it might teleport from here to here, and it won't realize that that's a block, even though it is a block. No real good way. I'm actually, there is a good way around that, but it is very complicated. It's another thing that I'm literally just working on earlier today. Anyways, that's not important. It's basic raycasting. It raycasts. It makes sure there's no block. The raycasting, it does not follow the trajectory. So again, the blue line is the actual true trajectory of the arrow. Red line is the one it takes. So obviously there's a little bit of difference between this, but this is 0.001 block of difference, so it doesn't really matter. That's why I think it's appropriate to, you know, approximate the line with raycasts between ticks. Okay, so now I guess I can talk about how I derived these equations. So, like I said, this is the main equation, and this, so the path function is made up of these, which are derived from these. Okay, and these equations are then, final time I'm going to say derived, they are derived from the data I collected. There's this Wikipedia page, and it's called Motion of Entities, and it has this nice little chart, and it's so helpful, you know. Oh, look, it's like a great and awesome. Wrong, incorrect. No, it's just not. It's useless. It's horrible. It might be used. It could be used, but I have no idea what these stupid numbers mean. Meters per second? What is then? Basically, this is useless. I had to completely get my own data. This is the data for snowballs. Basically what I did, stood at 0, 0, threw a snowball, threw it at a certain angle, recorded the velocity. This is per, so 20 is the tick that it's on. So this is not tick 1, tick 2, tick 3. This is every second, basically, because it's 20 ticks. As the snowball progresses, so after at the first tick, as I immediately throw it, it is going at 1 units per whatever. After 1 second, that's how fast it's going. After another second, etc., etc. That looks like it follows a pretty, traceable curve, and apparently it does. So the variables here is I was going, so the velocity y started at 0, velocity x also started at, 1 started 1. Terminal velocity for snowballs 3, and these things, they're a little off, but they follow it almost exactly. And so, by the way, these equations nowhere in this stupid document. Okay, I have the x velocity follows this exact curve. A is y velocity, B is x velocity, D, probably one of the, is drag. Terminal velocity and drag are all entity specific. For snowballs and arrows, it's both 70. It's extremely useful because then you can reverse engineer it and say, oh, well, at 20, it's at this point along the graph, and I can use that and approximate where the snowball will actually be. So with these equations, I can convert those into much more complicated equations using integrals, which I'm not going to get into very much because they're complicated, but basically gives you the position of x. Basically, these are the equations that approximate exactly where it is. But what is but this is Minecraft, okay? Everything's cool when you can have it in a nice simple equation like that, but you can't do that in Minecraft. Also, you can't do fractional powers, which was a big problem here because 2 to the negative t over d is difficult to approximate in Minecraft. T, by the way, is just the number of ticks. After 20 ticks, it'll be at this point right there, etc. So what I did, you can take this integral and you can make it way simpler, but by simple, I just mean not have the actual integral in it. I plugged this into Wolfram Alpha, it did some calculations, and it spit out this, which is uses natural logarithm of 2, and it also does this still. I wish that was taken out. I wish that could be changed, but I cannot. I'd like to point out this equation, these two equations are basically the exact same as these two equations. It just looks different. Sorry, these two equations. So these two equations are what I ended up with given my data, given these lines, how to approximate them, how to approximate the position. I got these two equations. Those are the lifeblood of what makes this thing work. What this Datapack does, calculates these equations for every single position along there. It calculate y value. This is literally just this. It is doing that. Okay, that's what it's doing. And this, like I said before, it is finding these individual values. You plug in all the variables, you plug in all the variables to it, and it spits out this or the y value of these dots, and then you plug in all the variables to this one and it spits out the x value, plug them together, you get a dot, and it follows the trajectory, right? Then this right here calculates z value, which is basically the exact same as the x value right here. It's just it's kind of complicated to explain, but basically it just moves it to 3 dimensions. Okay, you're gonna have to look that up yourself if you want to know more about that. I don't know how to explain it. This was a big part too. 2 to the negative t divided by drag. 2 to the negative t divided by drag. This part right here, I took forever trying to figure this out. I was like, how am I supposed to calculate this using Minecraft and scoreboards? It just doesn't work. You know, you can't just say 2 to the negative t. You can only use multiplication, addition, division, etc. Okay, you can't do 2 to whatever. So what I ended up doing was using an iterative function. What iterative functions do is they take a value and then they can just multiply it by itself over and over and over again. T is the only variable that changes. So t is the number of ticks that have elapsed. When this is equal to 1, so if that t is 1, that's what it gives out this value. And if t is equal to 2, it gives out this value. That's the only thing that changes between all of these. So that tick has the exact same equation as this, except for this t right there, it changes to 1, 2, 3, 4, 5, 6. And then it spits out that value. The good thing about powers like this is that definitionally, I can just say 2 to the negative 1 over 8, and then multiply that by itself as x times. The way the exponents work is that you just add them, which is perfect for this. Thank God it's perfect for this. Otherwise I would have no idea what to do. So I can just multiply these x times. If I want 2 to the 2 over 8, I can just do this value, which by the way is constant. So it's equal to this. This is the thing that it is equal to always. I can multiply that by itself, which gives me 2 to the 2 over 8. What I ended up doing, in this function called router, it gives me the value of 2 to the negative x over whatever that is for that specific entity, because drag is directly determined by the entity that you're shooting. So if you have an arrow, which is entity type 10, that the drag is equal to 70. So what I can do 2 to the negative 1 divided by 70, and that gives me 0.9901. and that's how I approximate it. Then to get the next tick, I just multiply that by itself. So I'd multiply it that many times, and I can just do that over and over and over and over again, and I get that value right here. I just multiply it by itself that many times. Every time it repeats itself, it multiplies that times itself that many times. Basically, all I'm trying to say is that it calculates this. At the end of this function, I've gotten the x position, I've gotten the x position, I've gotten the y position, I've gotten the z position, which you can't see here, but I've also calculated that, and then I move it finally to its position. I check if it's in a block, like I said before. If it's in a block, then I stop. I say, okay, we're good. It's in a block. I put a slime there, and things over. If there's not a block there, then the raycast forward, I'm at this dot right here. I put a marker entity right there. I look at that second point, and I start moving towards it in tiny, tiny little increments, way smaller than this. I move from here to right there where my cursor is, to right there, to right there, to right there, to right there, in constant little increments. And then finally, when I reach there, I stop, and then I do the same thing between here and there. And again, if there's a block, like, see those grid lines? Think of those as blocks. They're not actually to scale at all, probably, but think of that as a block. If it intersects a block, then I say stop, put a slime there, put a marker, stop everything. The way that I'm able to know when to stop raycasting is I actually use distance. So I find the distance between the 2 points along the line. I move it along as long as the distance is, and after the distance gets to that much, I stop, and then I'm good. After I do that, I do an action per tick. So this happens every single tick at where it is. I can just make it particle end rod. Every single tick, it will have a little dot, so it'll show you where it's landed, or where it is at that point in time. Anyways, something else that I've done is that you can have in-betweens. There's also that raycast between them, so this red line, not just the red dots, and that red line can be executed at right here. So this happens at every raycast location. See how there's so many more, it's like a solid constant line, because it's raycasting at a constant rate. Look, see how far between those ticks are? So there could be like 2 blocks in between that, and I wouldn't realize it, in between those 2 ticks. Good thing about the checking in between with raycasting is it finds approximately all the blocks in between there. So now there's basically no empty space. You can also you can change the runtime. Set that to how many blocks you want. That's how far it will go. If you do it to like 1000, it just basically won't stop until it reaches something. Then it sets itself to the amount of ticks before it hits the ground. So if you look on the right, the amount of ticks before it hits the ground is the score that the projectile has. So 41 ticks before it hits the ground. Something you can do is you can do... So this will just always remove 1 score per tick of every single arrow in the world. And since it gives you the ticks before it hits the ground right when it spawns, the arrow spawns, that means that you can, every time you remove a tick, it's like a countdown. So when that reaches 0, it'll hit the marker. So again, on the right side of the screen, actually no, I have my face cam there, that thing right there, you can see the arrow, and right when it reaches 0, it hits the entity. You can set I don't know, you can set if you're doing a TNT block, you can set its fuse to be the number of ticks before it hits, so it explodes immediately as it hits it. By the way, this doesn't work with entities. I could really easy make it work with entities. You could make it work with entities, but right now it's only hits blocks. So if you have an arrow and it'll shoot through an entity. So it does. So if I summon like a creeper, it'll say it'll go past it, but even though it won't, it'll just go through it. Again, you could really easily make this work with entities. You could just have a check say okay. Now he has like a little protector guardian slime. It's not very accurate, but it works enough. This is something that I haven't finished. Like I said, this data pack is not completely done. I said I'm not working on this anymore. I was going to see which side of the block it's on. And if it's like a TNT block, then you know when a TNT hits a wall, it bounces, but then doesn't stop. It goes towards the wall, it hits it, and then it keeps going. Let me just demonstrate. Okay, so basically, when a TNT hits a wall, you see how it like bounces off and then like doesn't stop going? That's what I wanted to fix and make it so that you could actually see where it'll go. Because right now, if you just have that, it'll say it's going to hit right here, right there. But obviously, it's not going to hit right there. It's going to bounce off. It's going to fall down. Continue to do that. I got bored. I said, you know what? It's not worth it. I don't really care. That's what could have happened. That's pretty much it. I think it is 5 a.m. right now, so I've been explaining this for a while. Distance between two ticks. Take over everything. Calculate entity. Repeats. Ends. Yeah. All right. Cool. Well, that's about it. Thanks for watching. I'll just turn it to Seth playing there.